Hello, Algebra 2 students. So here's a review video on 8.4, which is transformations of the reciprocal function 1 over x, and 8.6, which we just spent some time talking about radicals, nth roots, and rational exponents, a way to represent those with exponents. I'm trying something different here in this video. Because I've made too many email accounts to use the app that I use. So pardon me if I'm like slow. So you're just seeing a screen cap of my computer and I'm using a mouse. So first I'm going to start with radicals. So this is the fourth root of 81x to the 13th. So product property says I'm allowed to split this up into the fourth root of 81. See, this is a mess. Times the fourth root of x to the 13th. Meh. Okay. And now I can tackle these things separately. In the fourth root of 81, you're thinking, what to the fourth power equals 81? That's how you evaluate that. And it is 3 to that power. So the fourth root of 81 is 3. And now we have to do the fourth root of x to the 13th. Now this doesn't simplify perfectly. There's like nothing I can raise to the fourth power that gives me x to the 13th. So what I'm going to do for that piece is split it up into, oh look, I can change colors. Let's pick this color. I don't know why. The fourth root of the highest multiple, so like x to the 12th is what that would be. Highest multiple of 4. And then, oh, this is so slow. I have an x left over. And then this fourth root of x to the 12th I can actually evaluate because I know, I'm thinking, okay, what to the fourth power equals x to the 12th? And since power to a power you multiply, that would be x cubed. And then the trick to find that quickly is to just do 12 divided by 4, and this becomes x cubed. I made the brush smaller. And then I'm left with the fourth root of x. And that's equals, and this is equals. Done. And that's as simplified as I go, and I can't take the fourth root of x. If this exponent, so this is a 1, is less than the n, the index, you're done. Coolio. Next. Next example, I have a product of two radical expressions. They're both being, it's both the third root. So the third root of x to the 8th, third root of x to the 4th. Yeah, I could simplify those separately. But what's going to be easy for me is if I use the product property and I combine that and I say, okay, well this is the third root of x to the 8th times x to the 4th. And when I multiply with the same base, I add the exponent. So that's 12. And then I can simplify this right away. This is just 12 divided by 3 is x to the 4th. So I know x to the 4th to the third power equals x to the 12th. So that's that answer. Cool. All right, now let's talk about should we do a quotient? You'll be okay. All right, so let's do some rational exponents. So let's say you wanted to evaluate this. 64 to the 2/3. So I know with the rational exponent m over n, the denominator signifies the nth root, like what root I'm taking. So this is really the third root of 64. And I could make it 64 squared on the under the radical, but I'm going to put it on the outside, because I can take the third root of 64, so it's going to help me to do that first, and then square it. And the third root of 64 is 4. So this equals really 4 squared, which is 16. Okay, so in order to simplify rational exponents, write it as a radical and see what you can simplify. Because you know how to simplify these radicals, like what you have to think, like what cubed to 64, 4 cubed to 64. And then you can raise it to whatever power. The only thing that would be different is, let's say I was taking the cubed root of negative 64. Just realize that that would be negative 4. Not that you don't end up with the same answer, because when you square it, it still becomes positive 16. But negative 4 to the third power is negative 64. So that's why that would match. If you started out with, it would have to be like this. If I were to change the problem. If I just put a negative on the outside, that would just throw a negative on the outside of the 16. Okay, another one is going from radical form to rational exponent form, and that's just like the process of rewriting it. And sometimes you can simplify. So let's say like if I had the third root of negative 27 to the fifth power. So this whole thing to the fifth power. So yeah, I can find that right now. It's just negative 3 to the fifth. But it just says write it as a, like pretend the directions just said, write with rational exponents. Negative 3 to the fifth would work. So let's make this like a number that doesn't work. Let's make this like negative 37. Get my eraser. So like you can't simplify that without a calculator. It's 37 prime. And then so this is negative 37. And then this is the power, the 5. And then the 3 goes in the denominator because it's the root. You should be fine with just being able to do those for tomorrow. Again, like I mentioned, we're going to do more with radicals and make them more complicated, like with rationalizing denominators, rationalizing, and all the good stuff that was scary, but you'll be pros at eventually. So now I'll talk about transformations of the reciprocal function. What's nice about me doing this on my computer, I was trying to figure out stuff. Look at that. No, I'm confused. Is this still recording? Oh, it is. Hold on. Give me a minute. Okay, what's good is I can play with Desmos. So you have your reciprocal function 1 over x. That's what we noticed. And it has the vertical asymptote x equals 0. So I would make this a dotted line. And I have the horizontal asymptote y equals 0. And I'll make that a dotted line. Should have did that at once. Cool. Now, look at the table. We pick these two. This is for 1 over x. This point, -1, -1, 1, 1, and then my 2 asymptotes to determine the shape. So that's like all your parent information. That's the original. We're going to see how it translates. Okay, so that's all the parent information. It has these 2 branches, and it always looks like that. How do I make this go away from the table? I don't want it to be a table. I guess I'll rewrite it. 1 over x. Come on. What are you doing? 1 over x. There we go. And you could have reflections, but we never dealt with that. Just know it's possible. All right. So what we did is we did things like we would stretch it. Like that's a stretch by 3, by 4, by 5, by 6, by 7. Oh, that's 8, 9, 10. That's what stretch looks like. So let's say we stretch it by a factor of 4. Okay, and we want it to move to, I'll make a transformation to the left 5 units. Ooh, let's zoom out here. So now instead of x equaling 0 as my asymptote, now it's at -5. Right, so any horizontal shift will move the asymptote. And notice how the vertical stretch didn't affect anything. It was that shift. And let's say I wanted to move up 2. Okay, so now my horizontal asymptote isn't at 0, now it's at 2. Cool. But now where did these points -1 and 1, 1 go? So every point, I'm graphing this one, the function there. So every point, the x, you take away 5, that moves it to the left 5, and the inside's always evil. The inside of the function in this case is down here, underneath. I don't know if you can see my cursor or not. I guess we'll find out later. And then the y value, don't forget to multiply by the vertical stretch. This is whatever 4 times y, that'll stretch it, and then move it down 2. So when you describe the transformations, make sure you say the vertical stretch before you say up 2. Did I say down 2? Up 2, because then it would be different. So I would just always say the vertical shift last, like up 2 should go last. All right, and then the points end up at -6, -2, and at -4, right? And 1 - 5, that's right, and 6. All right, and we saw that our asymptotes, see x equals 0, x doesn't equal 0 anymore because every x value I subtract 5, so it's at -5. And then my horizontal asymptote, this horizontal line is now, I multiply this 0 by 4, it's still 0, but then I add 2, it's 2. And let me just verify that. I have the points -6, -2, there he is, and then -4, 6. So you would plot these 2 points and then stay within the bounds of your asymptotes to get a sketch. Right, and this was a transformation, just so we recognize it, of the parent graph, just 1 over x, that purple graph here. So it moved to the right, up, and stretched. Well, it stretched, moved to the right, and then up. Order matters. What else do I want to say about this? I want to say domain and range about this. So the domain is everything but the vertical asymptote. So domain would be -infinity. VA is -5. Union -5 to infinity. Oh, it's really slow goings with this. What do you call this? A mouse pad? I gotta figure something out here. And it's all parentheses. And then the range would be -infinity. Don't include the horizontal asymptote, right? Because there's never a y value of 2. No matter how many inputs you try to put in, you'll never get an output of 2. Union 2 to infinity. Wow, that's an awful infinity. It's like an ant. Here we go. Now it's an ant. And he's gonna eat this picnic. I'm not gonna draw a picnic. That is a picnic. So that should be good. Just identifying domain and range, knowing the vertical stretch doesn't affect your asymptotes. Draw it well, do the point mapping correctly. What's my search? That's interesting. Okay, the end. Images for the end. That's a good one. What do you think? This is the end. Oh, I like this one. This one's pretty. Ta-da!